hopefully you took some time to think for yourself, but let's talk about this position versus time graph. So when we talk about position being 0 means that we're at our home base, right? We're at our start point, all right? So from my start point, it looks like I moved 2 in the right direction, then I moved backwards till -3. Then it looks like I just kind of chilled out for a while, right? My position didn't change. I was just hanging out. And then I started to head back towards home, right? So again, this 0 line, when we're talking about position, 0 represents home, whatever that home or that start point was. So when are we moving to the right? Well, moving to the right means that V is positive. Well, velocity is positive when the slope of position is positive. So we were moving right from time 0 to 2 and from time 5 to 6. When is the particle moving to the left? Well, by definition, a particle moves to the left when the velocity is negative. How do we see velocity in a position graph? We're looking at the slope. Where do I have negative slopes? That's going to be between 2 and 3. When is the particle standing still? So we stand still when we're just at a slope of 0, right? Standing still would be that V is equal to 0. So we're standing still from time 3 to 5. We also have this brief moment where V is not 0, but V is also undefined, which again creates a critical number, right? This relates back to derivatives. So a critical number is also happening at t equals 2. We have this brief moment where we are standing still, all right? Then, where does the particle change directions? Well, we change directions when we switch from positive slope to negative slope to positive slope. So, I'm going to change directions at t equals 2 and at t equals 5. Now the question comes up, why isn't 3 critical, right? Because 3, we have another place where our derivative would be undefined, a critical number. But picture what's actually happening here. And I tried to put together a running man that looks like this, okay? Here's the play. I didn't quite get the start that I wanted to, but I tried. So he's moving to the right, turns around, moves to the left, hangs out for a while, and then turns back, okay? So again, picture running. You run to the right of your house, then you run back past your house, right? Because this is home. Past your house, then you just like take a little rest. And then you turn to go back home. Okay? So again, that's if we're based off of a position graph. This would be like given f, right? The original function, the OG. This, though, is going to be more common for us, where we're given the velocity graph. And the reason this is more common is that in calculus, velocity is our derivative layer. And we know that AP loves to ask about derivatives because then they can ask about second derivatives and original functions and forwards and backwards and all of those things. So now that we're looking at a velocity graph, this 0 line no longer represents home. This 0 represents resting, right? Because if velocity, which is what I'm looking at, if velocity is 0, it means I am resting. I'm not moving, just chilling, all right? So where does a particle move forward? Well, a particle moves forward when velocity is positive. Here's velocity. I'm looking right at it. Where is positive territory? Anything above the x-axis. So velocity is positive from 0 to 3, and from 5, we'll say this graph ends at 6, okay? But these would all be places where velocity is positive. When does the particle move backwards? Well, by definition, a particle is going to move backwards when velocity is negative or less than 0. Here's negative territory. My particle is in negative territory for velocity between times 3 and 5. Where is acceleration positive? Well, acceleration is v prime being greater than 0. So v prime would be the slope. Where do I have positive slopes? I have positive slopes here and here. So it looks like between 0 and time t equals a half, and then again from 4 to 6. Where is the acceleration negative? Well, acceleration is the same thing as the derivative of velocity, the rate of change of velocity, so v prime less than 0. That's going to be where I see negative slopes, right? V prime would be the slope of v. I'm looking at v. Where is that negative? So that's going to be between 2 and 4. All right, these next ones are interesting. We haven't looked at this yet. Where is the particle speeding up? Where is the particle slowing down? Well, a particle is going to speed up when your speed is increasing, right? So speed needs to increase. Well, speed is going to increase if you are moving away from 0, right? Because your speed would be getting bigger. So how do I move away from 0? Well, I move away from 0 right here, right? I start at 0 and I move away. Then I also move away here and here. Okay. And then I'm back to moving away over here. So let's think about what these things have in common. The blue and the red means that velocity is positive and acceleration is positive. So we're going to speed up when v and a are both positive. So that's going to be between our 0 and 1/2, and then again between 5 and 6. Okay, so that takes care of like the red and the blue little intervals overlapping. This one, though, is interesting. This doesn't fit that pattern, right? In this situation, I don't have positive velocity and positive slope. I have negative velocity and negative slope. So also between 3 and 4, I was speeding up, and that's because velocity and acceleration were both negative. So what happens is we need our velocity and our acceleration to agree. We need to be moving in the direction in which we are increasing our velocity. Okay? Where does the particle slow down? Well, let's think about the flip of that, if you will. Particle is going to slow down. Gotta get a different color. Particle is going to slow down where your speed is decreasing, which means we're moving not away from 0, but we're moving towards 0. Think about when you're about to turn around. If you're out for a run, you have to slow down to then turn around. So we're going to move toward 0 or toward rest, okay? In this case, if I think about where am I moving toward 0? Here, right? I'm heading in the direction towards my rest point. And then here, I'm heading in the direction of my rest point. So from 2 to 3 and 4 to 5. And that's going to be because v of t and a of t are both, are disagreeing, okay? V of t and a of t have different signs. So what I mean by that is if you look at this graph, this first interval, v is in positive territory, right? Velocity, I'm looking at it, it's positive right there. However, acceleration is negative because I'm above the x-axis but with a negative slope. This one down here from 4 to 5, I am physically below the x-axis. So v of t is negative, but I'm going toward the x-axis, I'm increasing, so a of t is positive. So here, v is positive, but a is negative. Here, v is negative, but a is positive. Whereas when we had the speeding up intervals, we had v is positive and a is positive, v is negative and a is negative, v is positive and a is positive. So they were in agreement with each other. Okay? Now, the other way that you can go about finding speeding up or slowing down, and this is something we're going to continue to study, I told you this is just the intro to all the vocab, okay, is to actually draw the speed. We know that speed from our previous video, speed is the absolute value of velocity. So my speed graph is going to take anything that was negative and flip it positive. So I actually don't care about any of this down here. Okay? Here's my speed graph. Speeding up, speeding up, speeding up, slowing down, right? Speed decreasing. So you can always draw the speed graph and actually see it. But again, think about what was happening. Moving away, away, away from the x-axis, away, 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 versus moving towards the x-axis, okay, or towards rest, if you will. Where does the particle have the greatest speed? Speed is the greatest at the interval from 1/2 till 2, and then again at 4. So from 1/2 until 2, and then again at t equals 4. We're going to do a lot of practice with velocity graphs, so don't panic. This is the first one. Okay, but think about definitions. They will help you. All right, the velocity of a body at time t is given here. Find the acceleration. Well, the acceleration is the same thing as v prime. So 6t squared minus 18t plus 12. Find the body's speed. So I want to find the absolute value of velocity every time acceleration is 0. Well, I'm going to start by setting my acceleration equal to 0. So this will factor into t minus 2 and t minus 1, which means that my particle has acceleration of 0 when t is 1 and t is 2. But I want to define the speed, so I'm going to find the absolute value of v of 1 and the absolute value of v of 2. So this will be pretty straightforward. I have velocity written right up here. So I'm going to substitute in and take the absolute value. So v of 1, absolute value, 0. V of 2, when you sub in, you get negative 1, but you want to take the absolute value of it, so you end up with 1. When is the particle at rest? Ooh. Particle, by definition, is at rest when v of t is equal to 0. So I'm going to set my velocity equal to 0. Now, ways that you can solve a cubic equation. You could graph it and find a 0. You could do synthetic division to find a 0. You could factor by grouping if it would factor by grouping, but alas, this one does not. So I'm going to take the calculator route and say if you graph this puppy, you end up with 2 times where v is equal to 0. It's going to be at t equals 5/2 and at t equals 1. Okay? So I chose to use my graphing calculator to solve this. You end up with a graph that looks like this. Oops. 1, 2, 3. So we have a 0 at 1 and we have a 0 at 2.5. The last one. Yep, I'm almost out of time. Pausing and then I'll show my work. Pause. All right, the second derivative of acceleration, of a position is acceleration. Doing all this work, I've shown all the steps, should be straightforward. Chain rule, we end up with A. Ask questions if you got them. It's the first day of money.